At oxidation, we will be talking about oxidation, redox reaction, free chlorine versus ORP. Then we will talk about shortly about our Dryden aqua generator, which is a hydrolyzer. We'll explain this a little bit. And then we talk about problems with corrosion.
Yeah, and that might be really an interesting
yep,
topic for
absolutely.
you, you know, with our products, without our products, really where is corrosion coming from and which are the parameters that you should control.
Yep, exactly. And then we have a short DAISY case study. And as always, we take your questions at the end of the show. So you have an opportunity to participate. Please use the chat function to type in your questions as we go through the presentation, so we can answer them at the end. And as always, our sessions are recorded. You can find them on our website. And also on the website, you can find the program and the PDF slides or the PowerPoint slides in a PDF format.
And by this,
yep.
Yeah, maybe we also want to already mention, you know, we always have these sessions only for 1 week. But end of next week, we will upload all the existing sessions on our YouTube channel, so you can rewatch all of them. We wanted to create a little bit a scarcity, you know, that the people are following, like you guys. You're perfect. Our life is always the best, of course.
Yep.
But then it will be all on YouTube session. So please stay with us also for the next 2 ones. Then you also can get your Dryden Pool Academy certificate. But for the future, then you will always find, if you want to rewatch something, you will find it on our YouTube channel.
Okay,
good,
very good. So in order to talk about oxidation, we decided we start with the smallest that we could find. It's an atom. So how do we explain this? An atom consists of what's called a nucleus, and that this consists of neutrons, which have a neutral charge, and of protons, which are particles with a positive charge. And then we have an orbit, or several orbits, where we have electrons circling the nucleus.
So you call them shelves?
Yes.
Shelves. Okay.
Yes. So, example, we have water. Water consists of billions of water molecules, H2O molecules, so 2 hydrogen atoms and an oxygen atom. And if you look at how this looks, then you can see it has 8 protons, 8 neutrons, and a total of 8 electrons on 2 shells. That's just to explain what is an atom, how does it work. And now Dominic will take you to the next level, which is something I completely missed in chemical class.
This is why we are doing it.
Chemistry class.
We're not doing this for you. We're doing this for Philip.
I think I was asleep in that class. So
anyway. You will understand later on, you know, why it's important.
Yep.
I think it's interesting to know it later. So you have all the atoms, you know, you have in the periodic system, starts with hydrogen, etc., goes on. And here you have seven periods. And here you have the different groups. For example, this group here is the halogen group. Remember the 3 halomethanes? These are the halogens. These are the oxidants. And, you know, if you take, for instance, here fluorine, you know, it has 2 electrons in the first layer and it has 7 in the second layer. So it has 9 electrons and 9 protons. It wants to get to 10. It wants to get to the noble gas stage. It wants to fill this shelf to 8. They always want to have 8 electrons in the outer shelf. So in the first one, only 2, but in the other, all of the others, they want to have 8. And this is where this number here is coming from. In fluor, you see here 5.0. This is the electronegativity. This is the force with which fluorine. How you spell it correctly?
Fluorine.
Fluorine.
Yeah.
Like my son.
Yeah.
Fluorine. Okay. He has birthday, by the way, today. You know how fluorine wants to attract an electrons because it wants to come to 8. Here you see, for instance, neon, there is no electronegativity. It will not attract an electron. The same goes for chlorine. Here you see 3, right? It also wants to go to 8. Now, 2 things that we see, the electronegativity of fluorine is higher than the one from chlorine because this here is nearer to the nucleus. So the distance is smaller than it's here. You see here 3, and then, or if you go here for the oxygen has 3.5. It wants to get two electrons, but it only has 2 layers. So to make this, not to overcomplicate this, here you see high electronegativity, here you see very low electronegativity. So these elements want really to grab an electron, and this is why these are good oxidizers. They want to grab an electron. And this group is what we call the halogen group.
I almost fell asleep again, I'm sorry. No,
yeah,
just
good.
kidding. No, really, but I think, you know, your last sentence is really important. So the halogens that we have on the right, they miss they're 1 electron short, right, to get to perfection. And this is what makes them such good oxidants.
Yes.
Because they're really aggressively looking for electrons because they want to become a noble gas, but they will never get there.
No.
Huh?
And
as
you can see, chlorine is stronger than bromine, and iodine we are not using really in pool, it's just the chlorine and the bromine. The fluorine, is that what you have in your toothpaste?
Yeah, exactly.
So, yeah.
Okay, excellent. Okay, so let's talk about oxidation. What is oxidation? Oxidation means transfer of electrons, which means you have an oxidizing agent that takes an electron, because again, remember, it wants to become complete, so it's looking for an electron. And you have a reducing agent, which is, you know, a substance that has to give an electron. So it's releasing, donating, that's a nicer term, donating. It's donating an electron, right? So an oxidation is a chemical reaction in which a reducing agent donates and an oxidizing agent gains an electron. That's the definition.
Give us examples for an oxidizing agent and for a reducing agent.
Okay, so an oxidizing agent that we just mentioned could be chlorine. It could be a free radical.
Oxygen also.
Oxygen, exactly.
So these are these ones. They want to grab an electron. This is what you have seen with the high electronegativity reducing agent.
A reducing agent could be an organics, for example.
Urea or whatever.
For example,
so this urea will then be oxidized by the oxidizing agent, and the oxidizing agent will be reduced. It's a little bit strange that they call it like this, but
and I think another good reducing agent is iron, right?
Iron, yeah.
So,
iron.
You know, iron is oxidized.
So iron would be the reducing agent. Here you would have oxygen, and you form then, iron. Sorry for that.
That's your wife.
Iron oxide. Yeah, I guess it is. Okay, so also interesting to say, oxidation and reduction always goes together. Always goes together, and that brings us to the redox reaction. The reduction together with the oxidation, that's the redox reaction. I think we skip this and go to the ORP, because this reaction we can measure in the oxidation reduction potential, the ORP.
Exactly. So the ORP, oxidation reduction potential, measures how powerful this oxidation potential is. It's expressed in millivolts, and if you look at this here on the right, so we have oxidizers on one side, and we have reductants on the other side, or reducing agents on the other side. So if you add an oxidizer, then the ORP, the potential, will go up. If you add contaminants or reducing agents, then the oxidation potential will go down.
So ORP cannot give you an absolute value. You have 1 milligram of free chlorine. It's impossible. But we can say with this and this ORP, we have a really good disinfection.
Yeah. And again, these oxidizers are hypochlorous acid, hydrogen peroxide, potassium monopersulfate, active,
free radicals.
Free radicals.
Stronger and less stronger ones. Yeah.
Okay.
And on the reduction, chloramines, organics, cyanuric acid.
Yep.
By the way, also organic urine, things like this.
Microorganisms and so on. Exactly. Okay. So ORP is an ideal parameter to measure the hygiene in a pool. And let me explain you what this over here means. You see on the vertical here we have the ORP, the oxidation reduction potential, ORP in millivolts, and then here in the horizontal we have the kill time in seconds, and this is based on log3 reduction of E. coli. So basically it measures the time it takes to kill 99.9% of E. coli bacteria in this example. So if we look at this here, let's say we have 650 millivolts of ORP. That means the kill time to kill 99.9% of these E. coli will be roughly about 30 seconds. If we increase the ORP to 700 millivolts, then the kill time will be reduced to about 5 seconds, significantly faster. This is why, for example, in most drinking water situations, we have an ORP of about 65 millivolts. For pools, it's usually 700 or a little bit higher. I think, exactly. What is it in the US? It's 650 or is it over 700?
Yeah, the MAC recommends a minimum of 650.
650. Yeah. That's what I thought. So it's an ideal parameter to measure how hygiene the water is.
Now, ORP also depends on other factors. One of them is pH, one of them is temperature, and one of them is turbidity, zeta potential, and with this turbidity.
Yep. Let's
take the example of pH. We have here on the right side, we have a constant concentration of free chlorine, let's say 0.4 milligrams per liter. At the pH of 7.6, let's say we have a redox potential of 650 millivolts. If we keep the free chlorine constant on 0.4, but we drop the pH to 7, at 7, chlorine is more active than at 7.6. The redox potential will increase. In this example, we choose 720, maybe it's only 700. So it depends really also on the pH. And this is why I think it doesn't make sense just to control ORP. You always should regulate pH and ORP together.
Yeah. Now, there are a few other factors that have an impact on ORP. And this is what you see here. This shows the relation between pH, which we have here on the bottom, and the zeta potential, which is an expression of the charge between particles or also the turbidity of the water, and the redox potential, which is in blue. So if we have a neutral pH, then our zeta potential, or the charge between particles, will also be very low. This has to do because now you have particles that are attracting each other, they're forming bitter particles, they start to drop out, and the water becomes clear. So zeta potential is low. And as the water becomes clear, your ORP reading starts to go up. That's the blue line. That's why in a neutral pH, you have this picture of a low zeta potential and a higher redox. I guess clean water is safe water, in a way.
Yeah, well, that also has then to do with biology, but really here, this is just, let's say you have a high zeta potential, you have a pH of 6, you have 1,000 particles in the water. Now you neutralize the pH to 7, you drop the zeta potential. These 1,000 particles, let's say 100 particles always form one big particle. So you end up with 10 big particles.
Yep.
Then the redox potential to have 10 bigs is higher than you have 1,000 small ones.
Yep.
Not that important. Just, you heard it.
Yep.
And water temperature, of course. This goes back to session number 1. You know, at a higher temperature, you have bigger biological growth,
Yep.
and that is also infected in the redox potential.
Exactly.
Now that means what? That means, you know, if you use your ORP, let's say in your residential pool, and you start the season, the water is still cold, maybe the pH is still quite low, there is no really load in it, and you make your set point 700 ORP, you measure the free chlorine, maybe you measure 0.5. But 4 weeks later, you know, when your pool is 30 degrees, I'm not good in Fahrenheit, I apologize for this.
30 degrees is 90.
90 Fahrenheit, pH maybe went a little bit up. You might need 1.0, 1.5 free chlorine to reach this 700. And this is not a bad thing because, again, the ORP, Philip will explain us the difference, it really shows us the power of disinfection.
Yep. So ORP measures the disinfection power of the water. It does not measure a concentration, for example, of free chlorine. It also, as we just explained, depends on the load, the water temperature, and so on, which makes this really great for residential pools. On the other side, we have free chlorine, which is always an absolute measure. It's an absolute concentration. And it does not automatically measure the disinfection power of the water. So therefore, you know, as we know, it's a legal must in public pools. I think in all countries that I know, you know, free chlorine measurement and minimum free chlorine levels are a must. But ideally, it should be combined with an ORP controller as well.
This is how we do it in Germany, Switzerland. You know, we regulate the pools between 0.3 to 0.5 free chlorine, and we double check the disinfection, the power of the disinfection with ORP, and that should be 720. But again, you know, I think ORP, it's under, and of course, ORP is much less expensive than free chlorine. It's also easier to operate. I think for residential pool, it's absolutely perfect to use ORP. I just would maybe, you know, if you start up the season, go for 700, and maybe after 4 weeks, a little bit double check. And if you are then sky high with your free chlorine, maybe adjust it by 50 millivolts to the 650 that you mentioned. I think it's really good. Only if you have public pool, here öffentlich, that means public pool, or DAISY, in our DAISY Plus concept, you will see it. We promoted the water with 0.1 or 0.2 of free chlorine, and this you can't do with ORP. Also, ORP works not that great with salt electrolysis. It works, but you have to work with gold probes. And if you change to, it works on a constant concentration. If you go on a very low salinity, ORP, very low, I mean 500 milligrams per liter or 600 milligrams per liter, then ORP starts to play crazy.
Okay.
Yep.
Okay, so we have learned that different oxidants have a different potential to attract electrons, right? And this is what we show here. This is expressed in electron volts. You can see at the very top we have two free radicals. These are hydroxyl radicals, and this is atomic oxygen. This is also a radical. These two radicals have a very strong oxidation potential, so they are very effective at oxidizing. Ozone is also fairly strong, and you can see how some of the other very commonly used oxidants compare here.
And this here chlorine, that's even chlorine gas. You know, if you go for tablets, this is below
Even
1. This is not weak, but it's just the other are really, really powerful. And here we come to complete oxidation and substitution reaction. So if you have This depends, you know, what contaminant you have. You know, some of these contaminants, here we see an organic, you know, where you have this carbon, 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 double bonds, you know, always two electrons who like two hands who hold together. If you go in here with an oxidant, then it's relatively easy to break these double bonds. The stronger your oxidizer is, the more effective you're doing this. There are other bonds which are a lot more difficult to crack. Usually free radicals are able to crack them completely, but less strong oxidants, for example, chlorine, is not always able to do this, and then you have a substitution reaction.
Yep.
It's not that important, but again, what we see here, we have on the left, we have this organic with the hypochlorous acid. We are able to break the main bonds. Then we get to the methane, 1 carbon, 4 hydrogen. These bonds between the carbon and the hydrogen is very strong. And here, if you add chlorine, go one more, you're not able anymore really to break these bonds between the carbon and the hydrogen. Then you have a replacement reaction, a substitution reaction, where the chlorine is replacing the hydrogen, and then you form chloromethane, dichloromethane, and then chloroform. The stronger, again, the stronger your oxidant is, the less you have these substitution reactions, the more you have complete oxidation, where you really release the complete electron to the other side.
Yep, exactly. Okay, great. So we now come to the Dryden Aqua generator, or DHN. For those of you who have attended our DAISY session, when was DAISY session? 6, I believe, huh? 6. You know, we have a 3-step system. We have the filtration with AFM, we have coagulation and flocculation with APF. We use ACO to protect chlorine from the sun as a replacement for cyanuric acid and support the natural disinfection power of the sun. And we have a step 4 here, which is for the disinfection. We call this then DAISY Plus. Huh?
DAISY plus DHN, that's DAISY Plus.
Exactly.
And that stands on the slogan of swimming and drinking water, because if you're in a really well-designed pool, we go as low as 0.1 free chlorine for depot disinfection. We do the main, maybe you go on one slide more, we do the main, okay, back to, yeah. We do the main disinfection with free radicals. They are very short-lived, you know, before they enter the pool, they are gone.
Yep.
Then we need a little bit of depot disinfection, and you can do it as low as 0.1 milligram per liter. You can go higher, of course, but this is the minimum we experience that you can achieve. And we wanted to go to this because in Switzerland and in Germany, by law, the regulation for drinking water is less than 0.1 free chlorine. So in order to use the slogan swimming and drinking water, we went that low.
Exactly.
You don't have to go that low, but yeah.
Yep. Okay, so the bad news is the DHN is not available for sale in the US. We have not introduced it yet in the US, but the good news is there are low chlorine solutions also available in the US. For example, here's a product that I pulled from the internet. It's an Acorite S3, which actually starts working at a salt level of 800 ppm. So that's relatively low. So there are alternatives to it. In the following slides, we will be talking about the DHN, but some of that information certainly also applies to a product like this.
The DHN is produced from us from Hayward Iberica, so Hayward, Spain. And obviously they are a daughter company from Hayward, and more now this technology also comes to the US, and it's already available. So this is a really good equipment.
Yeah. So why do we say swimming in drinking water, right? This is an example from your friend Jimmy. From Polit, UK.
As I already mentioned, you know, in Switzerland, Germany, 0.1 is the regulation for drinking water, and we can operate the pools in this low level. This here is what he measured in the UK. So in England, in Bristol, in the hotel in the morning, and you see here the tap water is 0.45. And if you would be in Scotland, Edinburgh, you measure it, it's 0.9. So we are much better than drinking water.
And combine chlorine through the roof too.
Yeah. That's one of the problems we have there. We try not to use their water because it's contaminating our pool water.
And I know we have high chlorine level in some parts of the US as well. You turn on the shower and you can smell it coming out. So swimming, drinking water, that's the claim, right? So as Dominic said, the DHN really completes the DAISY and it completes the disinfection. So far we were covering this year in our sessions, we were talking about flocculation and filtration with DAISY. And we're now adding the disinfection oxidation with the DHN, which completes this.
I mean, to be clear, you can use any other oxidants, and it doesn't have to be salt electrolysis or hydrolysis. We just believe it's one of the very best solutions. You can work with liquid chlorine, you can work with cal-hypo, whatever. We just take this as an example.
Okay. You want to explain the main components here?
Yeah, no, maybe later.
Maybe we have. Yeah, just quickly, huh?
Is it not coming later on again? Yeah.
You want? Okay, we'll do it there. Okay, that's good.
So let's go back.
Okay.
So in this DHN, in this hydrolysis system, you split salt into sodium and into chlorine, but you also produce free radicals. Here, blue, the hydroxyl radicals and the atomic oxygen. Also some other ones that you find here on the list. And this is what we want to do, mainly to generate these free radicals and have more chlorine as a byproduct just for the residual disinfection or for the depot disinfection. These cells, and I guess it's the same with Hayward in the US, you have, mainly there are two different types of cells. One is bipolar cells and the other is monopolar cells. The cells are here, monopolar cells is always, you have on each plate, you have a pole. So minus, plus, minus, plus. Bipolar cells, you have a plus and a minus, and in between you have slaves. Advantage of monopolar cells is they are much more robust against calcium scaling, because if you get here calcium scaling and you have here the slaves and you change the polarity, of course it's not that easy to release this calcium. This is why Hayward Iberica started to produce these monopolar cells, because especially in their area, Barcelona, you have quite hard water. Now by doing this, they also find out, okay, this has another advantage. It's not just more robust against scaling, it also can work in a very different salinity. It can work actually with 0 salt. Okay, then you're not producing any chlorine. You can work it between 0 to 100 grams of salt per liter. So very big range. Now, obviously 100 grams, we are usually not using it. Well, there are these new float pools.
Three times seawater. Huh?
That's 3 times seawater. Where bipolar cells, you have to run them between 3 to 5 grams. If you run them at a very low salinity, as we will see, just with 1 gram of salt or magnesium chloride, then you produce much less. You produce less of chlorine, but a lot more free radicals. And this you only can achieve with these monopolar cells, because you can work them with high amps, low voltage, high amps. And it's really the amps, who split the salt or the water.
Yep.
Maybe you want to explain this.
Exactly. Here. So here to explain the difference between hydrolysis and electrolysis. We see this in this graph here. This is the concentration of our salt concentration as expressed as TDS, total dissolved solids. And we see over here on the left, the production of free radicals, and here on the right, the production of free chlorine. So as we increase our salinity, the production of free chlorine will go up and the production of free radicals will go down. And the opposite, if we go into a low salinity concentration, we're starting to produce more free radicals and less free chlorine. And this is exactly where the DHN in this area works. We want to produce primarily free radicals, which means the DHN does not have very much salt concentration, so it will split water molecules, H2O, into these free radicals, OH and O radicals that we have seen. While a salt chlorinator usually operates at these concentrations, it will also form a small amount of free radicals, but it will
if it's monopolar
primarily
cells.
exactly produce free chlorine.
Yeah, only if you have monopolar cells, because you need these high amps. But it's exactly what Philip said, you know, the system, the DHN or the Aquarite system from Hayward, you know, it will not, it's like man, like human being, especially like man. We always go the most easy way, right? So it's much easier to split salt than to split water. So if there is no salt available, you start to split water.
Mm-hmm.
And yeah, so we are running it roughly between 1 to 1.5 kilograms of salt. You can go lower, up to 0.5.
Yeah.
But the Aquarite system would be 800.
800, yeah.
800,
Yeah.
huh?
Mm-hmm.
Well, here you see how we are doing this. This comes on a plate, all mounted, and this system has a pH measurement with the pH probe, pH pump, suction lens. It has a free chlorine sensor. It has a temperature sensor and flow switch. This is the cell where you produce the free radicals and the chlorine. This box also will control your variable speed pumps, low filtration for night, medium filtration for day, and high speed for backwashing. As we explained before, we have here a dosing pump for APF, and then as an option, you know, mainly for public pools, you can have salinity probes, etc.
Mm-hmm.
So
Good.
quite really sophisticated, and it always comes with a Wi-Fi. And the beauty of this is that the pool owner always will have his values. He can control them, he can change them. You as a pool builder can have all your pools on it, and you see if they are smiling, then it's all good. If they're not smiling, you can have a look. So you have control over your pools.
Yep. What's very important is that you use a low salt chlorination system like the DHN or others in combination with DAISY. Because what's important is that only DAISY is capable of reducing the oxidation demand of the water to that level that then makes the concept of hydrolysis work very well. So always combine the two together.
DAISY comes first.
DAISY comes first.
Only with this you can reduce the oxidation demand by 80%, and then you need just a very small amount. This is how we are doing it here. Might be a little bit different in the US, but you know, as a concept, I think it's really it's good. It's really good. It's the best that we know, and we have the experience in many countries. Okay.
How many units have we sold?
Thousands.
Thousands.
Yeah.
Okay.
Okay.
Yes.
Next.
So summary: drinking water.
Drinking water.
What we just.
This is how it looks like. And now the next one. This is how it can look. You know, this is a photo that we got from a customer from the UK, and he was complaining. He said, "My water is gone." No, he was not complaining. He said, "Wow, you know, you even do not see that there is water in it." This is how clean, how good you can get it, and you can't do it better. I mean, really, you can't. It's impossible. So it's much better than drinking water. Okay.
Are there any problems with the DHN or with salt chlorination?
There is one concern, and that's corrosion. You know, it's not a no corrosion risk; it's a low corrosion risk. You know, and I'm 30 years in the pool industry, and I learned all the time, Dominic, it's just the chlorides. You have to control the chlorides. If you're above 600 milligrams per liter of chlorides, then you will have a problem, you know, with stainless steel, even if it's 316L. And this was what I was taught, and this is also what I said, and this is what most people here in Germany, etc., say. You know, 600 milligrams of chlorides, that's the maximum. If you're above this, you have a corrosion problem for a 316L. 304 is only 200. And if you want to go higher, you have to go in a higher quality. I even can't spell it. This you
Austenitic stainless
yeah,
steel.
it's a duplex. It's a duplex one.
Yep.
But ladies and gentlemen, it's true. The chlorides play a role, but it's only one role out of 5 factors. And I think this is the important thing.
Yep.
I think salt and magnesium chloride, we don't go too much in this.
So, huh? Yeah. But basically, these are the 2 salts that you can
Yes.
add, that you can use.
Yeah.
They both have certain advantages, disadvantages. I think we have one more slide that we quickly talk about this. But
Okay.
so
Terminology.
so we were using different terms now. We were talking about salinity, which is often expressed as TDS, total dissolved solids. So these are all ions in the water that make up the TDS. Then there's chlorides, which we just talked about, which are measured as milligrams per liter. And there is, what else? Conductivity. Conductivity expressed in microsiemens. Now, how can you measure your concentration? What is the best way to do this? One simple way is to measure conductivity, right? Yeah. With a conductivity meter.
Exactly. And what is conductivity? Conductivity is how easy a current goes through the water, how easy electrons can pass the water. If you have water completely demineralized, there are no ions in the water, TDS is 0, current will not flow through the water. Only if there are some ions in the water, it really can flow through the water. And this measurement, how easy these electrons can flow through the water, this is called conductivity. And this you can easily measure with a very cheap $20, $10 conductivity meter, which measures this in microsiemens. To go and to count all the ions in the water, that's probably quite a challenging job. So you measure conductivity, you divide it by 1.6, and then you have approximately your TDS. This is how you do it. And this is also how we do it in the DHN. And if you take the TDS, divide it by 2, you have more or less your chlorides. Chlorides is this here, the Cl minus. To make an example, you have, I add 1 kilogram of salt to the water, let's say, and then I measure my conductivity. I measure 2000 microsiemens. Divided by 1.6, that will be roughly 1200 TDS. And that will be around 600 chlorides. Maybe we do then another example. It's a little bit boring, I know, but it's important that you understand these different terms.
For clarification, so when I read, that the salinity of a pool, like this low salinity, device starts at 800, that's referring to the TDS.
Yes.
Huh?
Yeah.
So
not to the chlorides.
Yes.
Here in Germany, we are paranoid about this chlorides, which is wrong.
Okay. This I think we can keep short, but I think it's still interesting. So basically, we have 2 types of salt. We have sodium chloride, which consists of 40% sodium, 60% chloride. As Dominic mentions, if you add 1 kilogram of salt in 1 meter cube of water, that's about 10 cubic feet, then your TDS will go up. So 2 pounds of salt in 35, sorry. Okay, now I got it. 2 pounds in 35 cubic feet of water will raise your TDS by about 1000 ppm. So now we have it. On the other side, you could also use something like magnesium chloride. Magnesium chloride also only has a 50% concentration. So you're only adding 500 ppms. But magnesium chloride has some nice advantages.
First of all, it has 2 chlorides molecules, so the percentage is higher, it's 75, but really the advantage, is this magnesium is 2 times positive charged. And that it's a kind of soft no-false, if you remember last session. It's 2 times positive charge, Mg++. and therefore it will coagulate negative charged particles that you have in the water, and it will make your water clearer. It also will coagulate phosphates. You know, if you add here 25 kilograms of magnesium chloride to your water in your private pool, phosphates are gone. Phosphates are gone. So, and then if you don't have phosphates in the water, you don't have algae problems. It makes your water really clear. It makes your water also blue. You know, if you have a little bit of iron in the water, you get a green color. With this, you get a blue color. And this is why we recommend to use 75% of normal salt, which is a lot cheaper, and about 25% of magnesium chloride. The other advantage, of course, for you, for magnesium chloride, by the way, we are not selling it in the US, we are selling it here in Europe, but it might be interesting for you. You can sell it at 4 times the price that you can sell salt, and it's something special, and it really makes, it's a benefit. And you can use it not just with the DHN, you can use it with any salt electrolysis system. And you can count it more or less the same, you know, you don't have to if you only use 25%, if you see, I need 4 bags, okay, 3 bags salt, 1 bag magnesium chloride.
Okay, good. So now we were talking about corrosion coming from chlorides or TDS, but obviously TDS is not the only thing that contributes to corrosion.
Yeah, there are more factors. And there was a gentleman, a French gentleman, 150 years ago, Monsieur Langelier, and he developed the Langelier saturation index. And here you see the formula. This is a factor, you know, coming from what it says, you know, what it says, you know, you should be around 0, that then your water is in balance. You know, 0.1 is okay, minus 0.1, plus 0.1 is okay. If you go higher, more than 0.4, and especially more than 0.8, the risk of calcification becomes very high. 1.0, you have a very high risk of calcification. On the other side, it's corrosion. So up to minus 0.4, it's okay. It's slightly corrosive. If you go lower than 0.4, especially if you go lower than 0.8, your water becomes highly corrosive. So we want to have the water in this area, let's say in this area. So how is this calculated? The water gets more here on the negative side, more on the negative side, the lower your pH is. So the lower your pH, the more aggressive becomes your water. It becomes more aggressive with decreasing temperature. So warm water is less corrosive than cold water. Hardness, total hardness, the softer your water is, the lower your hardness factor, the more corrosive it will become. And then alkalinity, the lower your alkalinity, the more aggressive your water becomes. And this is the last factor, the higher is your salinity. Okay, sounds complicated, it's not complicated. Let's make an example. You can go to there are different apps and websites, you know, just on Google, put in Langelier saturation index, and then my favorite website is you end up here on Lentec.
Yes. Okay. And again, as Dominic said, there's plenty of platforms, but this is a good one, a simple one. So we have here the 5 parameters that Dominic just explained to us, and we have an example here. So let's say we have 7.4 pH, a conductivity of or TDS of 1200 milligrams per liter.
That would be roughly 1 kilogram of salt, because 200 TDS you usually have, you have some calcium and magnesium in your water. So your tap water will already have roughly 200 TDS, maybe 400. You add 1 kilogram of salt, you're on 1,200.
So definitely
1 kilogram of salt.
Still a low salt.
Very low,
low salt. Then we have total hardness of 200 ppms. We have alkalinity of 100 and a water temperature of 28. Now this we could change here to Fahrenheit. 28 is roughly
90?
82. 82, I have it down there.
82. Thank you very much. So we click on calculate and then it will spit out the numbers. So you will see here the LSI is
This is 0.
0. The
Zero.
water is
Neutral.
perfectly balanced. It would also tell you if you had to adjust your pH here, which you don't have to because you're balanced. So these are identical.
It gives you the balance pH,
Yeah.
which pH you should go
Yep.
that you're in balance.
Yep.
We are balanced,
Yep.
all good.
Exactly. So let's change a setting here. We still have a 7.4, but now we raise the conductivity, the TDS, I'm sorry, to 2200.
So instead of 1 kilogram of salt, we have now 2 kilograms of salt. We have double the amount of salt.
Exactly. Huh?
And that means also your chlorides will now not be anymore 600, they will be 1200, right? So it should be highly corrosive, according to what my German colleague told me 25 years on, and this is wrong.
You should see rust everywhere, huh?
Yeah.
We're keeping everything else the same here, hardness, alkalinity, and temperature. And what do we get? We only get a very slight corrosion
balanced.
risk. It's
It's
basically
still
still
balanced.
balanced, huh? So
0.1 is still balanced.
we almost doubled our TDS,
Yeah.
but really the impact is almost neglectable.
And we checked it before on the website. We went to 5,000 TDS.
Yep.
And I think to what did we get, Florent? Minus 0.3, something like this. So
Very low, huh?
yeah.
Yeah.
Minus 0.3.
Yeah.
So what I want to tell with this, or what we want to tell with this, yes, salinity plays a role, but it's not the major role. Let's go to the next one.
Yeah, exactly.
Alkalinity.
So now we drop alkalinity from 100 that we had to 40. We go back here to the 1200. Everything else stays the same. And now we are starting to drop considerably. Now the water really becomes acidic.
Yeah. So in that case, I would now not increase my pH to 7.8, but maybe 7.6. So this hydrolysis system, we usually run them between 7.4 to 7.6. We know that chlorine works better at a lower pH. Free radicals don't care about the pH, but because of the corrosion risk, we would go there a little bit higher and we would increase alkalinity.
Yep.
So really alkalinity is the main driver. And
Yes.
alkalinity is consumed. It's consumed if you add an acid. It's consumed, just by evaporation, when the CO2 is gassing out, if you heat up the water, if you move the water, you lose CO2, then you drop the alkalinity. If you dose APF or any other flocculant is always acidic. So this is something that you have to bring in back to the water.
Okay. The other factor that also plays a role, fairly significant, is water temperature, huh? Yep.
Yeah, that's true. You see the same one, but in reality, it's not really this because you will not run all your season with 10 degrees. That
50 degrees Fahrenheit.
Yeah, that's a little bit chilly.
I don't think you'll use that.
No, you will not. And if you start it in these conditions and within a week you heat it up, then your pool is not corroded because it's just 1 week.
Exactly.
But what you can do, if you want to run it during winter time, just because it looks so good, to have your pool, but you're not heating it, then maybe just stop pH regulation, then automatically your pH will go to the balanced station.
So, my takeaway from the LSI really is, don't make the mistake to think that if you have a corrosion issue that it is just driven by TDS or salinity. It may be something else. And this tool here is really easy to use. You can enter those numbers and you will instantly understand where it's coming from, what you need to change also to get the water back into balance.
It's usually alkalinity. And maybe this problem is not as big in the US, because we have a lot of our parts, skimmers, etc. Most of them are stainless steel because they look better, or we have complete stainless steel pools. Now, I would not use these systems unless you control really this Langmuir index very, very carefully with a stainless steel pool. I mean, they are really expensive, and if they corrode, that's that gives big discussions. Who is responsible for this? So, but really the driver is, look at this alkalinity, and the main driver that you can change is here the alkalinity.
Yep.
Total hardness you cannot really change.
Yep.
Yeah, you can a little bit. This is what we discussed before. You know, this is the lime carbonic acid balance. This is how it is when you start the season. If you heat up then the pool and you use the pool, then you lose carbon dioxide. This carbon dioxide is missing, so pH goes up, alkalinity goes down. And also if you dose acid, you know, to bring back the pH, that also will decrease the alkalinity. And the only way how to bring it back is fresh water, if you are in a hard water area.
Yep.
And the second is the sodium bicarbonate, also baking, so maybe.
Yeah, also known as baking soda.
Yeah.
Huh? Yeah.
This is really good, you know, because if you don't have alkalinity, your pH will be very unstable, your water will be very corrosive, your free chlorine measurements usually plays crazy, depends on what sensors you have, but you know, most of the sensors, they are, if you're in alkalinity below 50, they give completely wrong readings. So alkalinity is something important.
And just a side note, if you want to learn something from for life, because that's something I learned when I prepared for this. So when you add baking soda or sodium bicarbonate to bake a cake, for example, it will react with water and with acid in the ingredients. And guess what? It will form CO2 that gases out, and that makes the cake rise. It's that simple. Huh? Okay.
So for the next session, he will bring a cake.
Yeah, we'll bring exactly.
So we come to the end. Case study, small. This is a pool where I learned to swim. So to share a secret with you, it's not 20 years. It's a little bit older. It was a really old pool, you know, with old steel filters, and we did change it to complete AC, new filters, complete AC, also with a DHN. This is a pool 5 minutes from here. It's a little bit our test facility, and yeah, with pesco valves and everything. And we also did, of course, added frequency inverter. We made massive savings in energy, you know, just with the filtration pumps, using frequency inverter, run them during nighttime at a low speed and at a medium speed during daytime, at a high speed for backwashing, you know, made a massive change. And also the fresh water per bather, we were before on 100 liter per bather, now we are on 32. These were massive savings, but I want to concentrate now on the quality of the water. You see, we have a combined chlorine of 0.15. Maximum value we are allowed to have is 0.2. Redox potential 750 with a free chlorine of 0.4, pH 7.3. Trialmethanes 15. I mean, this is milligrams, but usually you measure them in micrograms. 15, value is 20. I mean, this is very, very low numbers, very low numbers. This is really safe water. Here you also can make a baby swim. Chlorates that we talked in session number 5, you know, limit is 10. In Germany, it's 30. We are below 1. You know, this is absolutely incredible. And of course, turbidity below 0.1. You cannot measure it. The sensor says, I cannot measure turbidity. So this is how good you can do it. And really this, and you also see here the lights with stainless steel rings, no corrosion. You know, if you operate it right, it looks like this, crystal clear, no chlorine smell. I mean, you can't do it better. You really can't do it better.
Okay. Outlook, session number 8. Public pools.
Public pools. This is
an important one.
Yeah, this is my
Don't miss
this
it.
is really where we need you. I'm really looking forward. This is my favorite. We will look with you in 5 different ways how to treat pools, what you can do. Probably will not test out all of them. We again go quickly back to combined chlorine and THMs. We will give quite some time for UV medium pressure. We know they are very popular in the US for dechloramination, and we will tell you the pros and cons. Treatment with ozone, I think for the US, we keep this short or leave it out. And then last but not least, we will tell you a new story instead of UV medium pressure advanced oxidation process, which is used in water treatment for some years, not yet in pools, but it's cheaper, it's better, it's more sustainable than UV medium pressure. So we would love to have you